Okay, so this tutorial is to talk about skidding distance and the relationship between kinetic energy and speed. So first, a little explanation about kinetic energy and an important relationship that you'll need to understand for the quiz. So as a quick review, kinetic energy is energy due to the motion of an object. So if an object is not moving, it has no kinetic energy. And we can see that if we look at the formula. If this v, or the speed, is equal to 0, we don't have any kinetic energy. Okay, so from this, we can see that kinetic energy is proportional to the square of the speed, looking at this formula. So what this means is if I double the speed right here, then my kinetic energy has to go as 2 squared, or 4 times as much kinetic energy, keeping the mass of the object the same. If I double this quantity here, since I'm squaring the whole thing, it means I'm going to have 4 times as much kinetic energy over here. Same thing if I triple the speed. 3 squared, I'm going to get 9 times as much kinetic energy. So that's what we mean by the kinetic energy depending on the speed squared. So now we want to apply this to skidding distance. So if you're driving along and you have kinetic energy, how much braking distance do we need to leave? So the underlying principle here, as always for this unit, is that conservation energy is conserved. Oh, I just noticed I spelled that wrong. Oops. This means that the total amount of energy is never going to change. This is always true, no matter what. And it even applies to situations where we have thermal energy. So even though the speed is being lost from the object, the kinetic energy is being lost from an object and turned into dissipated energy or thermal energy, this energy just gets released into the environment in the way of sound or heat or things like that. And it can't kind of come back unless we do something else. So here's an example of a braking distance. So we have a guy here riding a little motorbike, and he's hitting the brakes and he's going to skid to a stop. So at position A, the driver is going to see the cat down the road. Takes the driver maybe half a second to react, so he's still kind of driving along. And then right here at position B, he's going to max out his brakes and he is just going to make a big skid mark along the ground here and come to a complete stop. So not hitting the cat, but scaring the bejesus out of him. All right, so what's going on here? So we talked about a little bit with the pictures, but let's put it into like our visual representation of using the bar graphs, and then we'll talk a little bit about the formulas. So at position A, this is where the car and the bike actually has the maximum speed and has not hit the brakes. So we have all kinetic energy here, and this is our total energy at the beginning. At position C, the bike has come to a complete stop. So all of that energy has been transformed into thermal energy. My total energy is still the same. This energy is just energy that's now heating the environment. So how do we get from here to here? How do we calculate that? Well, it turns out that the process of transforming that energy from one to the other is called work. So work is being done by the brakes to transform that kinetic energy into thermal energy. So now we have a little bit of formulas to look at. So our kinetic energy formula, we know it. The work formula is force times distance. So I just gave it a little bit more explanation for clarity. We're talking work done by the brakes is going to be the force of the brakes times the distance over which the brakes are applied. And this is going to be our skidding distance. So this is how that thermal energy gets transformed. So if we understand from the bar graphs that this amount of kinetic energy is exactly equal to the work done by the brakes, we can set these two equations equal to each other. All right, so here is our kinetic energy formula, 1/2 mv squared. Here is our work done by the brakes, which is going to represent our thermal energy lost. And we can see another square relationship, as we discussed in the beginning of this video, that as the speed increases, if this stays the same, then in order for this to be equal to each other, then the braking distance must increase too. So as speed increases, the distance must increases. And in fact, it's a squared relationship. So look at some examples, same as we did before. In a little driver's education, you'll be talking about this in a few years when you get your permit. You have to take your driver's ed courses. If you double your speed, double this, that means I'm going to have 4 times as much kinetic energy. That means I need to do 4 times as much work. Well, if the brakes aren't going to change, well, that means I need to give 4 times as much distance to stop. Same thing. If I triple my speed, triple it, that means I'm going to have 9 times as much kinetic energy over here. That means I need to do 9 times as much work on the other side. And if this stays the same, that means my braking distance must increase by 9 times. This is why the faster you drive, the greater the space you must leave between you and the car in front. So, moral of the story, little life lesson here. Don't tailgate, it's dangerous, and if you get in an accident, it's always considered to be your fault. All right, hope it helps.